currently he's currently focused on the learning of noises using psychoacoustical techniques, basically by measuring listeners' ability to accurately report aspects of the sounds. And he has been working on reaction times to natural sounds, showing that we are particularly fast to selectively respond to the human voice. So, thank you, Trevor.
Thank you. Thank you very much, Gustavo. And thank you, Mathieu, for the really useful overview to sort of set the scene for all of this. So Danielle and I were interested, like many people here, asking the same question: how on earth do humans make sense of such a complicated ordered environment, the kind of complicated ordered environment we find ourselves in all of the time, most of the time? And to get some kind of handle on kind of what are the features we use to recognise sounds in these complex environments, we thought it might be worth looking at the learning of new auditory memories. So we know that we must, to some extent, learn to associate a particular sound source, particular sound features, auditory features, with a particular sound source. But how do we even get this group of auditory features in the first place? Perhaps this is something we have to learn in itself. So these are the kind of questions we were asking, and we wanted to observe new learning happening. So to do that, we used noise, just white noise. The reason we went for this rather than a more natural stimulus, partly it's very complex. It's at least as complex as the kind of sounds that we're used to listening to in everyday life. And it has the advantage for us of being, in a sense, meaningless. One bit of noise sounds much like another, and it's not like words or the bark of a dog that would kind of tap into other types of memory. We're trying to get pure auditory memories here. And also, for a particular sample of white noise, we can be pretty sure that our participants have not ever heard this particular white noise before. It would be very unlikely. So we're starting from scratch. For those of you who are noise novices, this is what white noise sounds like. So it's just a hissing type sound. And if you ask listeners to remember that and compare it to other white noises, they give you a very strange look. So that's not what we did. Instead we kind of give them a foil, a kind of another task. Nothing to do with memorising not much to do with memorising a white noise. We asked them to detect repetitions, and this is a repeated noise. So I guess the way it was constructed was to take half a second of noise and then play it twice. So no silence in the middle, and listeners are asked to detect the repetition, which would sound something like this. Again, it sounds pretty much just like a hiss. But we give them a little bit of training. If you hear many more repetitions, it becomes a bit more obvious. So here's 10 times the same white noise. So when you hear it, you've probably got some sense of a churning, some idea that it was repeating. And we trained listeners in that and got them down to detecting shorter repetitions. Okay, so there's obviously a bit of learning in this, but not very long-term learning. What the listeners didn't know when they're trying to distinguish one of the ends, one of the unrepeated noises from one of the repeated noises, is that there was also a reference noise coming occasionally. So this reference noise was played twice to form a reference repeated noise, or ref-RN. I'll say ref-RN a lot today, so I'll introduce that acronym now. So when they first hear it, it's just another noise, and it's repeated again, so there's no way that they could sort of distinguish these two conditions. But further down the line, by the time you say you get to trial 6 there, they get to hear exactly the same ref-RN again. So they heard it there, they heard it there. All of the other noises, the N and the RN conditions, are completely different noises each time. So by default, you would expect if there's no learning, you'd expect on average across different blocks that the hit rate for the RefRNs would be the same as the hit rate for the RNs. So if there's no learning, we should see no difference in the number of times people think these are repeated. But if they do learn the RefRN to some extent, we might see that they get better at detecting this RefRN. To give you an idea of what it's like to learn a noise, you heard this before. And so that you've heard that noise quite a few times. Now if I just play you the 2 repetitions again, it now perhaps sounds a little bit different from the noise you heard the first time, so you have learnt some white noise. Okay, so we suggest that there could be a difference between the RNs, the hit rate for the RNs and the hit rate for the RefRN. There was, although the same RefRN is used within one block, each listener performed 4 different blocks, each of which used a different RefRN. So even if we got a particularly special RefRN, it should on average have cancelled out across blocks. And so it looks like our listeners are to some extent learning the noise. A nice thing, within the data we can get an idea of the rate of the time it takes them to learn the RefRN. And so to do this, we took out, say, all the first presentations of the RefRN from all the different blocks, from all the different listeners, and we can get an average hit rate for the very first presentation of the RefRN. We can do the same for the second time they heard the RefRN, and so on. And they heard the RefRN 50 times in a block, and so average them across all the listeners, and you get a bit of a curve, and you can see the learning of the RefRN as it happened on average across blocks. Does that make sense? Okay. And what we see is that by about the 10th presentation of the RefRN, the listener has learnt about as much as they're ever going to learn of it. There's a bit of a decrease for the hit rate for the RNs. These are different every time, which initially looks a bit strange, but it turns out to be more of a criterion effect. Listeners like to say yes and no in a sort of fairly constant proportion. So once they get more confident with the RefRN, they feel less obliged to guess when they're not so sure. So we see a decrease in the hit rate for the RN. We do have a follow-up experiment on that, but I was going to go into detail on that today. So focusing on this learning effect we see here, it doesn't look like very much on this graph. They start off getting a hit rate of about 50%. It's a pretty difficult task, but it only goes up to about 60, maybe a little bit more than 60%. So it's not a massive learning effect in terms of percentage hit rate, but there was a lot of variability between blocks. If I show you this block here, you see it's pretty much this is one block for one listener, and it shows the track of their responses. So in the first response they said yes, the second response yes, third response no, and we can show all 50 responses in this graph. And you can see here it seems like they're not giving any consistent response for this particular RefRN. But if we compare it to this listener, you can see that they sometimes said yes, sometimes said no for about the first 10 times they heard the RefRN. But then afterwards, they nearly perfectly said, yes, that's repeated. So here, in this particular block, it looks like we've got quite impressive learning, with just one error coming up, perhaps a slip in concentration, a wrong button. To get some idea of this sort of variability across blocks, we can take an average hit rate for a single block across the last 40 trials. So here it would be 96% or something like that. And we can plot a histogram of all those values. So that block is somewhere in here. So about 2/3 of the block fall in a fairly normal distribution, around about 50%. So here it looks like listeners are guessing, sometimes a bit more confident, sometimes a bit less confident. But then in the third of them, they're saying yes, that's repeated to the ref_rn nearly every single time. So we can take these two groups of blocks and plot the same graph you saw previously, but split into the two groups now, the two groups of blocks. And we see that there's these good blocks where they go to nearly 100%, and of course they do, that's how we selected them. But at the same time, this is like a third of blocks. It's quite impressive that they can learn white noise nearly perfectly in a third of blocks. And the half-life there is about 2 trials, so it's a very, very short rate of learning. And another strange thing is that for whenever they don't get perfect learning of the ref_rn or near perfect learning, we don't see any learning at all. So we've got this very sharp divide between either they're going to learn a reference repeated noise in a block, or it seems they never learn it. Okay, so summary so far, listeners can learn noise. They did this in an unsupervised fashion, so these are naive participants. We didn't tell them about the ref_rn, that there was any point in learning the noise in that sense. The learning seems quite robust to interference, in that, remember, when they were responding to the ref_rns, there were intervening trials as well, where they would hear a completely different noise, which was relevant to the task that they were doing. And we made sure that we never presented the ref_rn on 2 subsequent trials. So this learning is very robust to interference, yet it's extremely fast, where within a few trials they recognise it when they learn it, that is. Okay, so why did they learn some of the ref_rns but not others? I guess our first hunch was it's something to do with the noise. Some noises will be easy to learn, some noises will be hard to learn. But we didn't have the data for that because each listener heard 4 different ref_rns, so there's no comparison across listeners. So we did another experiment where we took 5 of the what we called good noises, in that they came from blocks where the listener had clearly learnt the noise, and 5 bad noises from 5 of the blocks in which it was quite clear that the listener was capable of learning, but they didn't learn this particular one. And 5 per listeners did these 10 blocks, and then after that continued on and did the 10 blocks again in a random order. So they did from their point of view, they did 20 blocks. From our point of view, they did the same 10 blocks twice, just to get some idea of within listener variability. And sure enough, they learnt the good blocks very well. It's quite a long experiment. They had lots of training, and we get very, very high sensitivities. This is a measure of sensitivity to the D prime. So for the ref_rns, they're clearly learning and getting much better responses than for the RNs. But they're also very good at learning the bad noises as well, on average. If we plot the first time each listener plot their performance the first time they heard it against their performance when they heard the same noise sometime afterwards, we see some consistency across that, but otherwise it was quite difficult to see any pattern. The different colours here represent different listeners, and the different letters represent different noises. And I won't give you too long to look at it, but we've been staring at it for some time, trying to find any pattern in it, and it seems just to be a bit of a listener noise thing. Some listeners learn some noises, some listeners learn other noises for whatever random factors we can't pinpoint. The good noises were a bit better on average than the bad noises, but this difference perhaps isn't big enough that we can go back and look at what were the differences in noise statistics, where it doesn't look like it would be too fruitful an exercise. When we looked at the time courses of learning in this, something seemed a bit strange. So here's the first run, when they did the first 10 blocks. So we can see at the start, same as the previous time course, the hit rate the first time they hear the ref_rns is pretty much the same as the hit rate the first time they hear the RNs, and then they diverge due to the learning. The strange thing was that on the second time, whenever they did their first trial of the ref_rn, it was already higher on average than the first trial of the RN. And we've tried to explain this in various ways, but the only thing we can sort of hold on to at the moment is that it looks like the listeners seem to have retained some memory from the first run going to the second run. We can't think of another explanation for this difference. Which is a bit strange because the mean time between this trial and this trial was 17 days, because they're coming back at various times to do various sessions. So these data suggest that the learning that happened here was sustained for over 2 weeks. Okay, so it looks like we have some fairly long-lasting memory here as well. At this point, these are starting to look like the kind of properties we would need for learning that is actually relevant to real life. So we've started off with this rather strange stimulus, white noise. But if your system is doing unsupervised learning that's robust to interference, and it's doing it extremely quickly, and these memories last, then surely this is affecting our perception in normal everyday life. If that's the case, then we would also need these noises to generalize to similar noises. Otherwise it wouldn't be that useful, because in the real world we never hear exactly the same thing twice. Or, well, not except in the most artificial of circumstances, like the laboratory. So we tried 2 experiments. Both of them had the same idea, where we give participants a chance to learn the noise, and then halfway through a block, or some distance through the block, we would replace the reference repeated noise with a changed version of the reference repeated noise. So in the first experiment, we time compressed the reference repeated noise, which also resulted in a frequency shift of any of the frequency components of the noise. And in another experiment, we reversed the reference repeated noise. For the time compression, we saw that if you shift it about 2, so this shows the sensitivity of the reference repeated noise, the RefRN, and the RN, and this circle here is the difference between the two. So we see, when we present the original to them again, you can see that yes, they had learnt it and they can still recognise it. When it's shifted when it's time compressed and frequency shifted to an amount equivalent to 2 semitones, they're still detecting it pretty well, and we see some continued recognition of it until it gets to about just over half an octave of 7 semitones. So it seems quite robust to small changes in the presentation frequencies and times. In terms of reversing the sound, we're a bit surprised that for the most part listeners continued to recognise the sound perfectly well when it was presented back to front. So from this we conclude that whatever they're recognising in the noise is probably something of quite short duration. They're probably not remembering the whole noise, but just a little slice of it. And when you reverse a slice of noise, it tends to sound pretty similar. Okay, so again, it's looking increasingly useful, this type of memory, because it generalises to similar sounds. I've been talking about noise recognition, but there's a slightly worrying alternative interpretation of this. Are they really recognising the noise, or are they just getting some very abstract, improved ability to detect repetitions, which is surely only relevant to laboratory? Recognition would be more relevant to the real world. And at first we couldn't see how we could distinguish these two, but then we realised that if we took the design we had before, so half unrepeated noises, half repeated noises, and of the repeated noises, some of the noises are 2 fresh half seconds of noise, and some of them are 2 reference half seconds of noise. We can take this and change some of the unrepeated noises. So here, half of them were the same reference sample of noise, but followed by a fresh noise, or vice versa. And this means that there's something to recognise, the reference noise, but it's not repeated, because the second half of the noise, or the first half of the noise, is a completely different sample of noise. So we wondered if we could trick the listeners, if they're using recognition, if they would incorrectly say that these mixed stimuli are repeated. So I'm just switching to the y-axis has changed to the probability of them saying yes. So it's hit rates and false alarm rates for signal detection theory complication reasons. And we see that sure enough they're learning the sound, they're reporting more repetitions for their FRN, and their false alarms are the least for the noise. But they have a lot more false alarms whenever we present the reference noise as part of the unrepeated noise. So it looks like we did trick our listeners into saying yes, it's repeated, even when they should have known even better that it wasn't, if anything. So it looks like our listeners cheat in this task. They use noise recognition, which is disconcerting for psychoacousticians, but from the point of view of it being relevant learning, it's quite a good thing that they're cheating in this way for us. So perhaps I've kind of set this up to suggest that they're confusing the mixed noise with the reference repeated noise. We can test that by getting rid of the reference repeated noise. So now they only hear the reference noise in an unrepeated context, and they've no particular reason to associate this with repetitions. We weren't that optimistic that this was going to work, so we also got the same listeners in different blocks to do the original task with the reference repeated noise, just to show that they were actually capable of detecting, of learning reference repeated noises. But it turned out that in the noises in the blocks when they never heard the reference repeated noise, they had a small tendency more to say yes, the mixed noise is repeated, even though they'd never heard this particular noise in a repeated format. So it looks like a very small difference. It turns out it is a significant difference. I think that happens because all of our listeners did this in one of their blocks. And it so happens it's the first block they heard, and it happened before they'd learnt any of the reference repeated noises. So it looks like there was a bit of confusion when they'd first learnt to do the task and they first learnt to hear a reference noise. They reported it as repeated, even though it wasn't. And perhaps later on, once they'd heard a real reference repeated noise, they were more confident that the mixed ones weren't repeated. So it looks like a small amount of learning here, but it's kind of hard to judge to what extent that learning occurred. But we do know they learnt something, and they learnt it in a context in which the noises weren't repeated. So again, this is quite good in terms of arguing that this type of learning is relevant to the real world. You don't have to use quick repetitions of the noise so that people can learn it. Okay, so how on earth is this all working? How are we able to learn such fast and stable representations of this noise? Because normally in computer models these two things are a bit contradictory as far as I understand. Either you can learn something quickly and it's simple and stable, and it's sort of it has to be simple, and maybe you will see rather unstable learning that might not be too robust interference, or you can get stable learning with much longer time constants. Here we see in humans we're quickly learning a very complex sound. We do know that such rapid changes seem to occur they are observed using audio physiology techniques in animals. So we do know that the representations of sounds sort of in cortex and potentially below are rapidly changing, pretty much as fast as you can measure them in animals. So there is sort of a neurological basis for these fast responses. And in order to perhaps speed up the learning, we wondered whether we could take some ideas from the reverse hierarchy type ideas. In reverse hierarchy, when you first hear a sound, you just get more like a gist of what the sound is. So when you first hear our stimulus, you might think, oh, it's a noise, but you might not pick anything else out about it, unless you're doing a task that involves really listening to the noise, in which case you might be almost querying your lower levels, asking, was there anything pitchy there? Was there anything rhythmic? And in that case, you're kind of doing a feature selection. You're kind of like asking for a smaller subset of features to look at. And that could be a way to pick out a smaller set of features which could be learnt more quickly and more stably. So we think this is the first example of perceptual insight in the auditory domain. By perceptual insight, I mean like very fast, lightning fast learning. A sort of a common example that's slightly analogous in the visual domain are these kind of pictures. I'm not sure if anyone can see what that is. If you've seen it before, it might give you an advantage. But once you've seen the original picture, you probably won't be able to stop seeing that as clearly being a frog. And if I show you the same picture in a couple of weeks' time, you'll probably see that it's a frog again. Maybe had somebody seen it before, I think, over there. So what's this got to do with CASA? Firstly, just thinking about perception of noises in the first place, this is a spectrogram of a white noise. And you can see that there's tons of detail in here. This is like an excitation pattern over time. And you can see there's lots of features that I think if you were looking at the spectrogram of the sound, you would see one noise as being very different from another noise. And this is something that's very different from our perception. In our perception, we perceive most noises as sounding very alike until we've had a chance to learn one. So I think a challenge for CASA could be to start perceiving noises as being dull, uninteresting stimuli, so that it's easier to separate out interesting things like speech from them. Another thing is that our experience of sounds clearly changes our perception of them. So maybe that's something that could be integrated. And here there's nothing too obvious here in terms of the standard Bregman segregation cues, yet people are still picking out features just through experience of these sounds. So in summary, we have a paradigm here for studying learning of new sounds using noise, which is easy to transfer to animals and computers. And this learning we observe has many features desirable for the real world. And to learn these, we probably need some kind of interplay between low and high levels. I'll just leave you with the list of properties that we observed for this learning. Have I left any time for questions?
Yes, we have. So we have a question there.
Hello.
Hello.
That was really interesting for me. I'm not from the subject, and thank you for your presentation. And I was just wondering, did you ask the participants if they had the feeling that they learned some noises? Or is it completely out of their perception?
No, I think listeners do often perceive that they learned something, and not always. I guess they're just looking for any way to do this very difficult task, and they don't know what they're meant to feel. Certainly, when we first did the experiment, some listeners during the experiment would pop their heads out of the booth and say, I think I'm hearing things. Sort of like they thought there was something strange going on, and they were right because they didn't know about it. So some listeners do voluntarily report that they have learned it.
Yeah, I was quite amazed, but I'm not from to learn that people can learn things without even knowing it. That's amazing to me.
Excellent.
Any more questions?
Did you? Yeah, it seems to me. I think you can hear. I think you can. Okay. All right. Well, did you check and see if what they were learning was something to do with the modulation spectrum? Because even in white noise, there are fluctuations in the envelope.
Yes.
Is that possible that that's what they were picking up on?
I guess it must be something to do with the individual features of these noises. If anything, noises have many too many fluctuations in the noise.
But if you're repeating them, the envelope fluctuations would tend to stand out if you're.
Okay, if you repeat them often enough.
Yeah.
I think other people have tried to link repeated noise detection to modulations without success, and certainly here we're seeing learning and recognition of these repeated noises in the absence of any repetition. So whatever they're detecting the noise has to be detectable even in the absence of even a single presentation of the noise. So I don't think it can just be the modulations that we introduce by repeating noise. Am I understanding your question properly?
So just as a follow-up of the previous question, so as a kind of a degradation, you try to reverse the signal, and I was wondering, like, to destroy the modulation information in the signal processing computer science area, we use a lot the bag of frame approach, where basically we destroy any temporal information by cutting the signal into frames and modeling it without any temporal dependencies. So I was wondering whether you could have a degradation that is actually chunking everything, flipping the chunks, and then repeat it again. So this means that in this case, well, it depends on the size of the chunk that you use, but it seems that the modulation information would be destroyed. So do you think that it could be an interesting experiment?
It sounds like a really good way to explore the size of the chunks that they are learning. So presumably if you start rotating very small chunks, then you're I guess there's a problem that at the edges, when you rotate it, you will be introducing some kind of artifact. It's hard to imagine that artifact in the noise domain, but you're kind of you're changing it into a different bit of a white noise at that point, and so you would still be preserving the bit in the middle in a reversed form. Yes, we could do that, and that would tell us something about the size of the bits of noise that they're learning. That could be useful.
Any more questions? We still have time.
Wow.
Just 3 minutes.
You can also use low noise, which is white noise, where you basically get rid of the modulation spectrum at all, and they have a very flat envelope.
Yeah, it's impossible to get a perfectly flat envelope and keep it.
I mean, it's, the fluctuations are almost imperceptible.
Well, they're imperceptible in white noise as well. I'm not too familiar with low noise, but I believe that works very well within sort of an auditory, like sort of set auditory bands. But I'm not sure if you looked at sort of a filter that included bits of two different bands, would you then see interactions between these bands and modulations in different places? I need to look into that further.
We have one last question. No? So one last question here. All right. Thank you.
Did you try to change the length of the noise sequences to see if there was better learning for longer or shorter?
We did actually, yes. So yeah, we tried to range from. We'd always used half-second chunks and everything I showed you there. We did go down to 1/8-second chunks and 2-second chunks. And what we see is that for the actual sort of the decoy task of repetition detection, it gets very easy for very short sounds. I guess if you get short enough, it's like detecting pitch, and gets harder for longer sounds. But people seem to learn that sounds pretty much sort of equally well.
And another question: do you think there might be a connection between so the listener's ability to learn noise and the rather well documented general ability of the human brain to identify patterns in completely random sequences? That's something that's been studied in psychology, especially studying superstition or things like that. When they give people a random sequence of zeros and ones and tell them it's the results of some sports team, and then people start interpreting it, saying, oh, here they run a run, and here they have a bad run, and things like that. Do you think that might be connected? Or?
I guess it is in a sense, in that people are getting random inputs and they are finding a pattern in them. So I wonder, would there be any predictions from the psychological domain that could tell us what kind of patterns are likely to be picked up on as meaningful in something that was designed to be meaningless. Certainly, yeah. Interesting thought.
Okay, so let's thank again Trevor. So